Good morning, everybody. I am going to talk about agroforestry and soil health. Actually, this will be two sections. Why soil health is important, that's what I am going to talk first, two slides. Then the role of agroforestry, how agroforestry can improve soil health. Within the last 10 or 15 years, you might have noticed there were some research papers published in good journals talking about the importance of soil health and human health. One of the simple example is if you don't have micronutrients in the soil, your body won't get micronutrients by eating those kind of vegetables and grain. So soils should have everything in the soil system to be healthy. So this figure shows soil erosion in Europe and America, USA. That was taken in 1997. Each red dot is 5,000 acres of highly eroded soil, HEL. Those are about 57 million acres. Yellow dot is 6,000 acres, non-highly eroded soil. They are about 1.57 million acres. So there is a lot of soil erosion happening in the US and in European countries. And some people have said these erosion values are underestimated. Those are about 3 to 40 times higher than the actual erosion, lower than the actual erosion. What happens when soil erosion continues? It takes nutrients to the ocean, hypoxia conditions happen. This figure shows increase of hypoxia conditions about 400% during the last 100 years. This is the same figure I showed you for US. As you see in Missouri, most of the erosion is happening in the north and northeast section. You see the density of red. The top figure is 2007, which shows some reduction in erosion because of conservation practices. And the Missouri, that is MDNR report, it says erosion was about 11 tons per acre in 1982. In 2013, it's about 5.5 tons per acre. That is reduction by 50% due to conservation practices. So what happens when you lose topsoil? This figure shows if it's a good soil like what we have at Hark, Menfro, yield reduction is about 13% for corn. Not a good soil like northeast Missouri, till-derived soil, yield reduction is about 30%. This study results came from Iowa, and that is the world scale. If you lose topsoils, you lose productivity of the land. And yesterday also a lot of people talk about population increase. Population doubled from 1927 to 2025, then it's going to double again. This section shows middle class, that white section. There were 2 billion people by 2000 in the middle class, but by 2030 there will be 5 billion people. So it's expansion of 3 billion people adding to the middle class. You know what will happen? The income prosperity increases. When your income increases, you start eating high quality food, meat and high level vegetables. This is a result from China. From 1990 to 2009, calorie increase has increased by 19%, meat by 2 times, vegetables by 3 times. So that means with the increase in population, you also need to produce high quality food. Just taking the numbers from US statistics, in 1950, average US citizen consumed about 6 ounces of meat a day. Now it's close to 9 ounces. If you take half the value, say 4 ounces, for that 3 billion people coming to the middle class, you will need to kill, slaughter 500,000 animals a day, every day, to meet the meat demand. So you know, we have to produce a lot of food, and you also need good land to produce this food. And we are losing agricultural land. This statistics shows 25, if we had 93 acres, now we have only 78 acres of crop land. Pasture, now we have only 86 acres. So that's a reduction in available crop land for agriculture. So another 41 million will be lost, 7% more will be lost by 2030. So you don't have enough land to produce more and also high quality food. So you can do all your techniques to improve plants, genetics, breeding, tissue culture, everything. But you need a good soil for that plant to survive and produce. Just like your racing car, sport formula car, that cannot drive fast on this lane. It needs a good road. Just like that, plants also need good soils. So we started two long-term studies. One is in northeast Missouri, Knox County. That's a corn soybean rotation with tree buffers. These dots are trees. On the middle watershed, on the west watershed, we have grass buffers. That's our control watershed. This is a picture taken. So all these watersheds have flumes, approach section, sampler collections, monitoring devices. That other one started in at Hark. That's a grazing system. That's a replicated study. This is a watershed study. That has two replications with agroforestry buffers, two with grass buffers, and two controls. This is how it looks in 1991. We had only topographic lines. In 1997, we installed those buffers on the middle watershed, trees and grass. On the west watershed, grass buffers only. So this is to give an idea about the growth of trees. These were planted in 1997. Now they are about 6 meters tall on average. So we looked at different soil quality parameters like soil physical parameters, chemical parameters, and biological parameters. One of the simplest example is if the aggregate stability is not strong, when you put a soil, it will separate into pieces, and that means high erosion potential. So on this study, we took samples from crop areas, grass, agroforestry, and grass waterways. As you see here, crop areas has the lowest aggregate stability. That means higher erosion potential, removing nutrients, and you are losing topsoils. Do you know how many years would it take to produce 1 centimeter thick topsoil? Does anybody know? 500 years on average. So a large rain event can remove 2 or 3 centimeters of topsoil. You may have noticed that some fence post. Nobody put fence post at an angle. You know, everybody wants to put a fence post vertically. So because of erosion, some fence posts are like this. So that is big erosion. That clearly shows within a generation that much erosion has happened for that fence post not to stay vertically. So we also looked at soil bulk density, which clearly shows when you have perennial vegetation, it has lower bulk density compared to the crop. That means more porosity, more water retention, and more water infiltration through the profile. So here it shows the difference. Very low hydraulic conductivity in crop, and the agroforestry and grass buffers have higher hydraulic conductivity. And that's at log scale. That's about less than 10 with the crops and more than 600 for the crop and grass and agroforestry system throughout the profile. So this is again the similar results from Hark grazing systems. You see continuously grazing systems has very low hydraulic conductivity compared to agroforestry systems. That means more infiltration, more water storage potential with the agroforestry integration. And we also took some soil samples and did X-ray work. Like human body X-ray, you take a sample, take to the X-ray machine at the hospital. So those are measured at 200 micrometer resolution. It's about 1/5 of a millimeter at the hospital. So this is about 10 micrometer resolution. So you can see all the pores, where the pores are located within the soil profile, are they connected, how long is the pore, how many pores are connected to each pore. We took soil samples from 0 to 10, 10 to 20, and as you see here, different depths. So this is the row crop area. These black dots represent soil pores. As you see, there are more pores with trees and buffers compared to the crops. That means more water storage potential, more potential to reduce runoff. And we did the similar study at Hark. This was a PhD student who was working with us from 2008 to 11. Now he's assistant professor in South Dakota. So we took samples and took to the hospital from 0 to 50 centimeter depth. As you see here, grass buffers, lot of roots near the surface. You see a lot of density, lot of porosity, and this is the tree system. And the continuously grazing, that means cows graze in that area continuously, more compaction,
more death of plants, so less spores. And we also looked at soil moisture patterns of these systems in the crop areas, grass buffers, tree buffers. That is, we had sensors at 5, 10, 20, 40 centimeter depths, and we continually measured soil moisture from 2003. So this is in the crop area. So we have 4 replicates for the crop area, 6 replicates for the tree. We also had 4 buffers. And now this area is biomass. So we know that soil moisture dynamics in crop areas, grass areas, biomass crops, trees, and all 5 days treatment. So what we see here is the top one is for 5 centimeter soil moisture from March to December. The top horizontal line is for the crops. Crops always maintained very high moisture content throughout the year. Perennial vegetation was transpiring more higher leaf area, so they had very low moisture content throughout the year. That means it can store more water when there is a rain event. And also we learned earlier improvements of physical properties, more porosity, more carbon. So that also helps store more water. During the rain events, we looked at 3 rain events, that the rainfall pattern during that period. First one, second one, and the third one. As you see here, more water is stored in the perennial system, the length of the bar, compared to the crops. So that's due to the perennial vegetation and improvement in soil properties. So this clearly shows perennial systems can store more water after a recharge event, and also maintains lower soil water content before recharge event, pre-rain events. So that is more potential to store runoff rainwater and reduce the runoff potential. This is the summary of all 4 depths. There is a thick clay pan in the area, so the effect of vegetation is minimal below about 35 centimeters. But trees still reducing the water content in the soil profile. So why does these things happen? If you know recent improvements in food production and grasses paid more attention to the above ground portion, then the root portion was getting smaller and smaller. This is prairie type grasses, much more deeper root systems, some even 12 meters. This is a tree system taken in 1927. So those things can help improve soil properties when we integrate agroforestry. Then we also started looking at different root distribution patterns. This is Kenny Bader, who was a technician at Hark until about 2012, right? 12 or 14, yeah. He was helping me to take soil samples. And we took soil cores and we looked at rooting patterns of trees. So we put, if this root is between 0 and 45 degrees, we considered those as horizontal. 45 to 90, we considered them as vertical roots. We looked at the proportion of vertical versus horizontal roots within a tree system. That means if you have a higher proportion of horizontal roots, that means those roots tend to go to the crop area and compete for moisture and nutrients. If a tree has a lower percentage of horizontal roots, those are better to reduce the competition. So as you know, crops had the lowest root density throughout the profile from surface to the 100 millimeters, 100 centimeters. Grasses had the highest and trees had the second highest root systems. So this is what I have explained earlier. If you look at the bur oak, they had smallest percentage of horizontal roots, only 44%, and 56% vertical roots. That means that plant tends to produce more vertical roots. So, and this is true for other plants. This is a study from Iowa. They looked at the carbon that shows the importance of selections of different tree species. If you select a poplar or willow type tree species, there will be more carbon in those systems. So, and what is the importance of carbon? If you increase this is the permanent wilting point. Below that, plants cannot take this water. This is the field capacity. Plants can take water between these two. If you have 1% carbon, this is the amount of water If you increase the carbon by 5 up to 4, the available water content doubles within the system. That's what we are doing with agroforestry. And selection of trees are important. As you see, hybrid poplar has larger biomass, and that means more carbon. And we looked at the biodiversity and different communities within the soil, enzymes, similar system with different management practices. This is a PLFA study looking at phospholipid fatty acid to understand total microbial biomass. Row crops at the lowest, grass waterways oldest at the highest. This is distance about 50 centimeters from a tree base. So all these had higher concentration of total microbial biomass. And also different communities, which shows gram-positive bacteria, gram-negative bacteria, saprophytes, fungi, everything was higher because of the introduction of agroforestry systems, trees and grass systems to the system. This is a study came from South America, which shows agroforestry has mean species abundance higher than the cropping systems. And this study shows about earthworms. Black circles indicate earthworm casts. Gray circles mean prune trees, tree canopy. As you see here, compare this corner versus this corner, much more lower number of trees and lower number of earthworm casts. Here, higher number of trees and higher number of earthworm casts. So that means when you have trees in the buffer system or cropping system, we have more earthworms. So there are so many benefits we can explain. This is a study conducted by a PhD student who evaluated antibiotic absorption capacity by different soils, and which shows agroforestry soils have much stronger bonding capacity of antibiotics compared to other soils. If you look at the figure there, we are using about 7.7 million pounds of antibiotics a year. In animal production industry, they are using about 30 million pounds per year. So the body retains only about 20% of the antibiotic. The rest goes to the soil or to the water. So if you adopt these kind of practices, they can retain those kind of antibiotics getting into the water. And selection of plant species are more important. And another student looked at thermal properties. So when you have perennial vegetation, it can buffer thermal properties. Like if it is a high temperature day, it has a buffering capacity. This is the soil thermal conductivity, how temperature transfer from the surface to the deeper soil. This is for the crop, much more higher thermal conductivity compared to the perennial vegetation. And thermal diffusivity also higher. And very low heat capacity when you have crop soils. That means when you introduce a buffer system like perennial trees, grasses, it has a much stronger buffering capacity against the temperature stress. And you know now climate change and how it's going to affect. So if you have perennial vegetation, those can help living communities in the soil as well as to reduce the carbon release from the soil. And you are at Missouri, I hope you remember, you can identify this figure. Who knows this one? This is the University Hospital, the parking lot next to the University Hospital. This plot was started in 1917, and that helped to develop soil loss equation. So University of Missouri has very strong historical background in terms of working in soils. And there are 3 long-term studies which can show. Sarah mentioned about this. Windbreak project started in 1935 till 42. They have planted 220 million trees. A recent study shows 2.5 to 4 megagrams per carbon hectare because of this windbreak project. And a similar project started in Canada. They planted 610 million trees. Because of that, greater than 218 megatons of carbon in the soil, and so many other services. And similar thing happened in Russia, started during a Stalin period. They have planted windbreaks on 5.7 million acres. So there are, as I showed you, most of the research results at smaller scale shows the benefits of agroforestry in improving soil health. These are large scale studies, and that also shows the improvements in carbon. Carbon improvement means all the soil properties will be improved. Better growth, better land productivity, water quality, everything. So if you have agroforestry on your land, that's going to help improve soil health and your health too. Thank you.
Good morning. My name is Elizabeth Rogers, and I am a graduate student and scientist in training at the University of Missouri. To put it very briefly, my research involves trees and pollution. And two of the main investigators besides myself that are involved in this research are Dr. Chung Ho Lin of the Center for Agroforestry and Dr. Ronald Zalesny Jr. of the USDA Forest Service. Before I begin and get into my research, I would like you to visualize something. So in your mind's eye, picture a landfill. I want you to picture all of the contaminants that exist within and around the landfill, whether they're in the soil, in the groundwater, in the runoff. And around that landfill, I want you to picture trees being planted intentionally, trees that grow very fast and have extensive rooting capabilities. What you are visualizing right now is represented in this photo right here. This is a photograph of one of our field sites. We have extensive rooting trees with rapid growth, hybrid poplars, planted next to a landfill. We have 16 of these sites established in our overarching project that I am a part of. And I would like to talk about my objectives as well in this project. My main goal as a researcher in this is to help expand what we know about hybrid poplars that are planted at landfill sites like this. The first phase of my objectives is to collect information on the ecophysiology and on the ecosystem services of these poplars at landfills. One of the main parameters that I'm interested in is water use. How much contaminated water are these poplars taking up as they're acting as biological pumps? When they grow, they take up so much water. I want to know how much water they're taking up, whether that's daily, weekly, monthly. In addition, I am interested in what particular compounds are in the contaminated water and which ones are being taken up more. Are there trends among clones? Once I have this information collected, I'm going to synthesize it and integrate it into a format that is relevant for different groups of people, whether that be researchers or site managers or the public, even including K-12 students. One of my passions is education. In 2019, I have had some preliminary accomplishments regarding these objectives. For one, I have begun my sap flow literature search. So I'm looking at the sap flow of poplars, whether that's at landfills or just in the forest. I have also begun to establish a leachate pollutant prioritization scheme, and I've collected some samples of leachate and groundwater from these sites, and I'm learning in my laboratory training how I will be analyzing these samples. And finally, I've established my experimental design for field instrumentation and data collection, which I will be starting this summer. And just to leave you with an image, we began with an image, we'll end with an image. Every city that's on this map, aside from Rhinelander with the star, has one or more of these hybrid poplar landfill sites. The ones that I will be focusing my research on are those that are circled in green. And I've given you an image of each of them, along with a date that the image was taken, just so you can visualize and really see how fast these trees actually grow. Thank you very much. Every along with a date and really see along with a date and really see along with a date and really see them 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 along with a date